These are the computed problems for the unit on solids, liquids, and gases. And the first one I'm going to do from chapter 12 in UIT. So chapter 12, problem number 1. And it says, find the density of a 5 kilogram solid cylinder that is 10 centimeters tall and has a radius of 3 centimeters. So here we have a radius of 3 centimeters. And then here we have a height of 10 centimeters. Doesn't look like a solid cylinder, but that's what I drew. I did draw it to scale, by the way, if you check out the squares here with the 3 and the 10. Okay, in any case, we have to figure out density. And the density is, of course, mass divided by volume. And in this case, the mass is given as 5 kilograms. And we have to figure out what the volume is. And it's the volume of a cylinder, so we have to look that up. And the volume of a cylinder is the height times the cross-sectional area, so pi r squared. And this is not hard at all to look up. So and that comes out then to 10 centimeters times pi times, that was supposed to be a times, oops, I made a mistake here, that's a squared, not cubed, it's squared, times the radius squared, 3 centimeters squared. So plugging that into a calculator then would be 10 times pi times 3 squared. I come up with 283 cubic centimeters. So 283 cubic centimeters. At that point I'm going to see that the units are going to look rather strange. We like to express it in grams per cubic centimeters. So I'm just going to take the kilograms away here, and instead we'll write 5,000 grams per 283 cubic centimeters. So 5,000 divided by 283. I come up with a rounded 18 grams per cubic centimeter. Perhaps this is an alloy. I looked up a list of pure metals, and either of the common ones, gold or uranium, are relatively close. So we either got a uranium cylinder here or a gold cylinder, I guess, whatever our preference is. Chapter 12, problem 4 says a certain spring stretches 4 centimeters when a load of 10 newtons is suspended from it. So there's already some information there. 10 newtons is apparently proportional to a stretch of 4 centimeters. That means F proportional to delta x, Hooke's law. Further on it says, how much will the spring stretch if an identical spring also supports the load as shown in A and in B? Well, in A they both share the weight, these two springs, and they're supposed to be identical, so each one of them supports 5 newtons, and therefore each one of them will stretch by 2 centimeters. Part B. Each of the springs has to hold up 10 newtons, so each of them will stretch 4 centimeters each. So this one is going to be 4 centimeters, and this one here as well is 4 centimeters. This can be shown with this animation. This would be here the original problem, and the numbers are going to be different, so I'm going to let the string stretch here. The other two on the right and left will also move, but just focus on the one in the middle. Right now it starts at 203, and then it kind of goes down and it goes to 223. So this string stretches here by 20 centimeters. Now the other strings, they're identical. That means that this one here and this one here are the same string over here. So as I said in the problem, in this scenario here, it would stretch half as much, 2 centimeters in the problem. Here it should only be 10 centimeters, and it goes from 203 to 213. So each of them is holding only half the load. The one on the left, these two springs are on top of each other. So with this one here stretching 20 centimeters, each of these should stretch 20 meters, so there should be a total being read of 40 centimeters. By the way, this little piece here, this connection piece, and here I made it virtually massless, very little mass compared to this one. So anyway, so this one here should stretch by 40 centimeters. And when you look at the number, indeed, that's what you can see. So each one of them stretches by 20 centimeters, which is the original amount of this one, and that's pretty much what I said in the problem that I calculated. The next problem is from chapter 13, and it is problem 1. And it says the depth of water behind the Hoover Dam in Nevada is 220 meters. So we have H equals 220 meters. What is the water pressure at the base of this dam? And it says in parentheses, neglect the pressure due to the atmosphere. I'll make a comment on that later. So we look up the equation for that, which says that the pressure equals the weight density times the depth, and we find that the weight density of water is 9,800 newtons. That comes from that 1 cubic meter of water is 1,000 kilograms, and then because of gravity we multiply by 9.8 times the depth, which is given as 220 meters. And when I do that on the side on a calculator, I come up with 2,156,000, or around it 2.2 million Newton meters, or the unit would be pascals. Of course, I only need two significant figures. If I don't want to write down a big number like that, I could also write this as 2.2 megapascals. By the way, the atmospheric pressure is 100,000 pascals, so due to the depth here, the water pressure is at the bottom is 22 times higher than atmospheric pressure, and I wouldn't neglect it, but what happens is that we would have atmospheric pressure on top of the lake, as the lake meet, and then we have atmospheric pressure at the bottom where the water is coming out. So atmospheric pressure is pushing in on the top, and it's pushing in from the bottom, and because it's pushing from two different directions, that actually cancels out, and perhaps that's what they meant by saying neglect. So the total pressure is actually 2.2 megapascals. So next problem is number 2, chapter 13, number 2, and it says a 6 kilogram piece of metal displaces 1 liter of water when submerged. What is its density? So it has a mass of 6 kilograms, and it displaces, when submerged, 1 liter of water. And an object that sinks will displace an equal amount of water volume of water equal to its own volume. So that means that as it displays 1 liter of water, its own volume is also 1 liter. So we do the density is 6 kilograms divided by 1 liter, which comes out to 6 kilograms per liter, or 6 grams per cubic centimeter. The reason is that there's 1,000 grams in the kilogram and there's 1,000 cubic centimeters in the liter, so the two conversion units cancel each other, and that's why we come up with the same number here. So 6 kilograms per cubic centimeter. Next problem is from chapter 13, number 4. It says a dike in Holland springs a leak through a hole of area 1 square centimeter. So the area is 1 square centimeter. Not tiny, it's about 1/6 of a square inch. And it goes on at a depth of 2 meters below the water surface. So h equals 2 meters. H or D. How much force must the boy apply to the hole with his thumb to stop the leak? And the story originates actually from an American novel that is called Hans Brinker or the Silver Skates, and it's set in Holland, and that a boy saves the town by pushing his thumb into this hole, holding the Atlantic Ocean back. And so the question is that actual possible? Could he do it? Well, let's see what the pressure is. Pressure, of course, is weight density times depth. So we have 9,800 newtons per cubic meter is the weight density. And we have a depth of 2 meters. So we come up with 19,600, or rounded 20,000 pascals. Now the force equals pressure times area, because pressure equals force divided by area. So we have 20,000 pascals, but that's in base units. So therefore the area also have to be in base units, and it's 1 square centimeters converted to meters means that we would have to divide by 100 centimeter per meter, and because it's square centimeters we have to do that twice, so squared. And when we do that, we come up 20,000 divided by 100, and again divided by 100, and we come up with just 2, with the units being pascals times square meters, which is newtons. 2 newtons, which we could convert if we wanted to pounds, comes out to roughly 0.5 pounds, and that's all the force that the boy has to exert. And so therefore, yes, he can easily do it. The next problem is chapter 13, problem 6, which says, when a 2.0 kilogram object is suspended in water, it masses, and masses is in quotes, 1.5 kilograms. What is the density of the object? So the mass is 2.0 kilograms, and now it says that the apparent mass, that's why they put that in quotes, is 1.5 kilograms, because this is really not the true mass, but it's the weight minus the buoyant force, and then the equivalent mass to that. So as the object is submerged in water, the scale reads only 1.5 kilograms. Well, the way this can be done is to say that since it is submerged in water, it displaces a certain amount of water. Well, how much? Well, apparently the buoyant force is equivalent to 0.5 kilograms, actually it's 5 newtons, respectively. The water that is being pushed out has a mass that is 0.5 kilograms, so water mass is 0.5 kilograms, with water having a density of 1 kilogram per liter, or 1 gram per cubic centimeter. Then the volume of water being pushed out is also 0.5, in this case liters, and because the object is submerged, that means now that an equal amount of water is being displaced, so V equals 0.5 liters, and therefore the density is going to be the mass, the true mass of the object, 2.0 kilograms, divided by its volume of 0.5 liters, which comes out to 4 kilograms per liter, or 4, that's an equal sign, 4 grams per cubic centimeters. Next problem is chapter 13, number 7. And it says, an ice cube measures 10 centimeters on a side and floats in water. 1 centimeter extends above water level. If you shaved off the 1 centimeter part, how many centimeters of the remaining ice would extend above water level? I just took a picture here of some icebergs in Portage Glacier in Alaska. And if we have 1 centimeter above water of a 10 centimeter ice cube, that means that 9 centimeters is below the water surface. In any case, no matter what you do, is you have 10% is above the water and 90% below the water. And if you shave 1 centimeter off, now you have a total of 9 centimeters, and you still have 10% above, or 0.9 centimeters, and 90% below, 8.1 centimeters. And that's due to the density of ice, which is 0.9 grams per cubic centimeters, and that tells us that always 90% is below the water, 10% above water. The next problem is chapter 13, number 10. And it says, in the hydraulic pistons shown in the sketch, the small piston has a diameter of 2 centimeters. The larger piston has a diameter of 6 centimeters. How much more force can the larger piston exert compared with the force applied to the smaller piston? That's Pascal's principle, and as the areas is proportional to the force on Pascal's principle, if we have a certain force on a small area, for example 10 newtons, and I'm just making this up here, for an area of pi times r, which is 1 centimeters squared. And now we look at how much force we would get for an area of pi times 3 centimeters squared. And notice that the diameter is 3 times as much, but the area comes out to be 9 times as much because the radius is being squared, and so we come up with 90 newtons, and I should have written a newton there as well. So the answer is 9 times. The next problem is chapter 14, number 1. It says, what change in pressure occurs in a party balloon that is squeezed to 1/3 its volume with no change in temperature? That is Boyle's law, where we have P1 times V1 equals P2 times V2. This problem says no change in temperature. And I left some space there, you'll see in just a moment. So it occurs in a party balloon and is squeezed to 1/3 its volume. So 1/3 its volume. Well, the equation needs to be correct, left and right. This is the original pressure, original volume. This one here is the final volume, so we need to have the final pressure. So the pressure increased 3 times. And of course, we notice that as we squeeze a balloon, the volume gets smaller, but of course the pressure gets larger. The next problem is chapter 14, number 4. It says, estimate the buoyant force that air exerts on you. Parentheses, to do this, you can estimate your volume by knowing your weight and by assuming that your weight density is a bit less than that of water. It says, in first word for this problem is estimate, which means that the answer I'm going to come up with depends on what my weight is and perhaps some estimations that I'm making. So that means that you or somebody else may not come up with the exact same number I come up with, but we should all come up with the same ballpark figure. Okay, so first, my mass is 90 kilograms, and this would be me or a Norman peasant standing on a scale. So for next I'm going to figure out, well, my density is roughly that of water. I know it says a little bit less here, but let me just use that. It's roughly that of water, which means that my volume is also 90 liters because there's 1 kilogram to the liter for water. Now this is my volume. As I'm submerged in air, so to say, I'm sinking in the air as low as I can. Obviously I'm not floating. The displaced volume of air is the same as my volume. So I displace as much volume of air as what my volume is. So air V equals 90 liters. Now I'm looking up how much mass of air that is, or I'm going to compute that. So I'm looking up what the density of air is. So density of air equals 1.29 kilograms per cubic meter. That's a relatively small density. Usually when we had the densities for solids and liquids, we were in the neighborhood of a few thousands kilograms per cubic meter. Here we're at only 1.29 kilograms per cubic meter. Makes sense. Air has relatively little mass. Still, that's 2.5 pounds for a cubic meter, or roughly 30 cubic feet, top of my head. Okay. So next thing is that the mass of the air that I'm displacing is the density times the volume. So 1.29 kilograms per cubic meter times 90 liters, but my volume units need to match, so I'm going to have 0.09 cubic meters because there are 1,000 liters in the cubic meter. So the air that I'm displacing comes out to 1.29 times 0.09, which is around at 0.1 kilograms. And multiplying that by 9.8 meters per second square gives me 1 newtons, which is the weight of the air that I have displaced. That's also the same as the buoyant force. So this one here is the weight as well as the buoyant force. So 1 Newton, and when I divide that by the conversion unit of roughly 4.5 or 4.4, I come up with 0.2 pounds. And keep in mind that it is estimated. That is the buoyant force that the air exerts on me, which is also the weight of the air that I displace. So compared to my 200 pounds of weight, that's relatively small and probably negligible. The next problem is chapter 14, number 7. It says, on a perfect fall day, you're hovering at low altitude in a hot air balloon, accelerated neither upward nor downward. The total weight of the balloon, including its load and the hot air in it, is 20,000 newtons. So the weight of the balloon is 20,000 newtons. What is the weight of the displaced air, and B, what is the volume of the displaced air? Well, A, the buoyant force that is produced by the air on the balloon has to equal the weight, because the balloon, as it says, is hovering, and then they added it's neither accelerating up nor downward, so the two forces have to balance each other. So the weight is pulling down at 20,000 newtons, and the buoyant force is pushing up at 20,000 newtons. So that's part A. Part B says, what is the volume of the displaced air? So since the weight then of the displaced air is also 20,000 newtons, I would have to divide that by the density. So volume equals the mass of the air, which is 2,000 kilograms, because a weight of 20,000 newtons is divided by 9.8 or 10, so it comes out to 2,000 kilograms, and then needs to be divided by the density of air, which is 1.29 kilograms per cubic meter, and then 2,000 divided by 1.29 on the side comes out to 1,300 cubic meters. This problem is a little bit different than the last one, because here we have a floating balloon, and something that is floating will displace as much air as it weighs. While in the last problem I was submerged in air, and when you're submerged you're displacing as much volume as your own volume is, just like Archimedes' principle says. Okay, next problem is chapter 14, number 8. I'm going to do that as quickly as I can. To squeeze it into these 10 minutes. How much lift is exerted on the wings of an airplane that have a total surface area of 100 square meters when the difference in air pressure below and above the wings is 4% of atmospheric pressure? So the force comes out to the atmospheric pressure times the 4%, so 0.4 times area. So atmospheric pressure is 100,000 pascals times the 4% times 100 square meters, and that comes out to 400,000 newtons, or 400 kilonewtons.